Hello everyone, in this video we'll take a look at asynchronous FIFO. We'll first understand what is the need of asynchronous FIFO, what is the application and why do we need to study about this asynchronous FIFO. Second, we'll take a look at the architecture. We'll understand what are the different blocks present, what all do we need in order to implement asynchronous FIFO, both from your architecture perspective as well as the code perspective. So we'll discuss the pseudocode and we'll understand how the entire implementation is done in Verilog. And the fourth case will be, we'll also understand a very important topic, which is FIFO depth. What is this FIFO depth? That will maybe solve one or two simple numericals on this. And in these sections of architecture as well as code explanation, we'll also understand few points which are extremely important while we are understanding what is asynchronous FIFO. First is what is metastability and how asynchronous FIFO solves this problem of metastability, as well as we'll also understand why gray coding is preferred in uh, why gray coding is preferred over binary coding in asynchronous FIFO. So we'll answer all these questions so that you get a complete picture of what goes on in asynchronous FIFO, what is the implementation, and what are the different architectural choices. Why do we make these choices while we are implementing the FIFO? So the first question we need to answer is what are the application areas, or why do we come up with asynchronous FIFO? We could have simply just worked with a synchronous FIFO. Okay, synchronous FIFO is when your clock domains are safe. When you read clock domain, when you write clock domain are similar. For example, let's say I have a SOC and there is only one clock domain, and this is one block and this is second block, block A and block B, and I want to transfer data between block A to block B. Now, since this entire SOC is working at one clock, which is never possible, but let's assume hypothetically that this entire SOC is working at same clock domain. So what happens is when you want to transfer the data, you simply have a read domain and a write domain, and both of them are working in the same clock domain. This can be simply implemented using synchronous FIFO without any hassle. But what happens when you have different clock domains? For example, in a SOC, you might have a CPU, you might have different peripherals. For example, let's say this is a UART for serial communication. Okay, or this can be your timers, ADC, DAC, or any SD card interface. So this is your peripherals and this is your CPU. So I need my CPU to run at a very high speed. So that means the clock, this is working at a clock domain, let's say 1, and this clock domain, in this clock domain, the clock frequency is higher because I need my CPU to work at a higher frequency. But the UART or the peripherals, I don't need them to work at the same frequency as that of the CPU. So that is in a different clock domain, let's say clock domain 2. Now, the problem is I need to transfer the data from my CPU to my UART, but the problem here is both of them are working at a different clock frequency. That is, this is maybe running at hundreds of megahertz or sometimes even gigahertz, and this UART may be of few megahertz. So the problem is the CPU is producing, whenever you want to transfer the data, my CPU is producing the data at a much faster rate than the rate at which my peripheral is consuming the data. So this production speed is much higher than the consumer speed. So what happens? There will be problems. For example, some of the data might be lost because since the data production is faster, but I'm consuming it at a very slower pace. Somewhere in between, if there is no proper storage in between, my data might get lost. So that problem is being solved by asynchronous FIFO. We'll discuss how FIFO depth comes into picture in this case, because whatever extra data the UART is unable to consume is being stored in this FIFO as, and based on that only we determine what is our FIFO depth, how much data is required to be stored so that my UART doesn't miss any data reads. Okay, so this is one point. The second point is, since both of them are working at different clock speed, the UART might sample the data at near the clock edge. So this might lead to setup violations, hold violations, or it might also result in something known as metastability. What is metastability? That means you are sampling the data very close to the edge, violating the setup and hold time, because of which you are not getting a clear 0 or 1. So your sample data is fluctuating between 0 to 1, and in order to solve this metastability, we use synchronizers in our asynchronous FIFO. We'll discuss what is synchronizers and why do we need, how many flip-flops do we need for synchronizers, and why 2 flip-flops are needed for synchronizers or more than 2 flip-flops are needed for synchronizers. We will discuss that later in the video. But for now, understand that metastability arises when you are transferring the data from two different clock domains and the data is not being stabilized to a clear 0 or clear 1. It is fluctuating between 0 to 1. In that case, we might need something to solve this problem. So this problem is completely, I won't say completely because metastability cannot be completely solved, but the probability of occurring metastability perfectly reduces in asynchronous FIFO, because there is also one formula for MTBF. We'll discuss about that also, mean time between failures. So that is also one criteria for which your metastability might reduce with two flip-flops. So all these problems, all these cross-domain crossing, cross-domain data transfer, clock domain crossing, and the data transfer between two different clock domains, the problem of metastability, and the problem of the disadvantage in binary coding. All these will understand what are the disadvantages in binary coding. All these problems are solved using asynchronous FIFO. So that is the reason why people have moved on from synchronous to asynchronous. Based on your application, your architecture will also change. So next we will discuss about the architecture. So we'll understand the architecture very briefly. So there is this domain 1, which is the write domain, and there is another domain which is read domain. So we have the data in which is coming from domain 1, and that is to be passed as data out to the domain 2. Now there is write enable. Write enable is for your write clock domain, and write enable, whenever this is asserted, this means I need to write some data to the FIFO. And whenever this read clock domain read enable is asserted, this is with respect to your read clock domain. Whenever this is asserted, this means you can read the data from the FIFO. So W clock refers to your write clock, and this R clock refers to your read clock. So all the operations which are done in domain 1 is with respect to this W clock, and all the operations which are done with in the read clock domain is with respect to the R clock. So all the operations in this domain is with respect to R clock. All the operations in this domain is with respect to W clock. Now we'll understand the full flag and the empty flag. So in order to determine whether you can write the data into the FIFO further or you cannot read any more data from the FIFO, that is to be specified with the help of full. What does full flag tell you? The full flag tells you that I cannot write any more data into the FIFO because my FIFO is already full, and that full flag is determined in the write domain. So this you should remember, that the full flag is determined in the write domain. And in the FIFO, if you are unable to read any more data because your FIFO is empty, that empty flag is determined in the read domain. But for this full flag, I need both the write pointer as well as the read pointer. Similarly, for this empty flag, I need both the write pointer and the read pointer. Now, what is the problem here? In the full flag, I already have my write pointer, which is synchronized to W clock. And since my full is determined in the write domain, there is no problem in obtaining the write pointer. But the problem arises when you want to obtain the read pointer. You cannot simply fetch the read pointer from your read domain, from your read clock domain. Reason being, that is working at a different clock frequency, and this first domain is working at a different clock frequency. So if you need the read pointer from the read clock domain to be passed on to the write pointer, to be passed on to the write clock domain, then you need synchronizers in between. So we'll take a look at this line. So we have this binary pointer. The binary read pointer is converted to your gray read pointer. So we have previously discussed why we are moving on with gray pointer instead of binary. We'll take a small example and understand why gray coding is preferred over binary coding. So for now, just remember that this gray pointer, this binary pointer is converted to gray pointer. The gray pointer is passed through two flip-flops. These two flip-flops are nothing but synchronizers. And why do we need synchronizers? Because we are passing the data between two clock domains. So the gray pointer, the gray read pointer is synchronized with respect to the right clock domain, and then that is passed in order to determine the full flag. Similarly, for read in the read clock domain, in order to determine the empty condition, I already have the read pointer easily because the read pointer is working with respect to the read clock. But in order to determine the write pointer, that has to be passed from a different clock domain. So what I'm doing, whatever binary write pointer is there, that is converted to gray write pointer. That gray write pointer is passed to the synchronizers. This is also synchronizer. It is synchronized with respect to the read clock domain. The write pointer is synchronized with respect to the read clock domain, and this synchronized write pointer is passed to determine the empty condition. Okay, so whenever you're passing signals across the domain, you need synchronizers in between. And since in order to determine the full and empty condition, I need cross domain signals, that's why I have put these synchronizers. Okay, and W reset n is the reset for the right clock domain, and R reset n is the neg h reset for the read clock domain. Okay, so the main important thing is the full is determined in the write domain, empty is determined in the read domain. For both these flags, I need write pointer as well as the read pointer. But with respect to the domain, whatever pointer is available, that that pointer has to be compared with a pointer in the other domain. So in order to safely pass the pointer from the other domain, we have placed synchronizers in between, and that is how the synchronized pointer is then compared with the pointer of that domain, and then the flag is being determined whether it is full or empty. Okay, I hope this architecture is clear. Next, we'll discuss about why do we need gray coding instead of binary coding, and then we'll move on to the pseudocode and we'll understand how these empty and full conditions are determined and why do we need both the pointers in order to determine full and empty. So let us first understand why we need gray coding instead of binary coding, why gray coding is preferred. So previously we have seen while discussing the architecture that you need the pointer information from one domain to be passed on to a different domain. And while passing those information, you're passing it through a synchronizer. And the pointers are converted from binary to gray. So why are we converting these pointers from binary to gray? Let's say your pointer position is initially at 3. So 3 in binary is represented as 0, 1, 1. So now what happens? The pointer, a new data write has come to the FIFO. A new data write request has come to the FIFO. The pointer will increment to position 4. And what is position 4 in binary? 1, 0, 0. So you can see that from 0, 1, 1 to 1, 0, 0, how many bits have changed? All the 3 bits, all first bit, second bit, third bit, all the 3 bits have changed. Okay, so I know that this information of pointer has to be passed into from domain 1 to domain 2. While passing from one domain to the other domain, there are chances that all the bits are not correctly all the bit information is being passed. What I'm trying to say is, if my pointer is at, let's say, 0, 1, 1 and it is supposed to produce 1, 0, 0, but only my first bit is correctly changed and my rest of the bits remain same. My rest of the bits have not yet changed. But uh, what will my second domain infer? My second domain will infer that my pointer information is 4 instead of, sorry, it will infer my pointer information is 7 instead of 4. So what happens? This tells me that my FIFO is full, whereas I was only supposed to obtain the value 4. My FIFO is not actually full. It wrongly represents FIFO as full because all my bit changes have not been propagated to my domain 2 correctly. Okay, so why I'm saying FIFO as full is, let's say your FIFO depth is 8. So whenever you obtain the pointer position to be 7, you say that your FIFO is full. This is an assumption, okay? So you are wrongly getting value 7 instead of 4 because all your bit changes are not correctly propagated, because of which it is resulting in a misinterpreted pointer value. That is the problem in binary coding. So how come this problem is solved in gray coding? In gray coding, how do we represent 3? 0, 1, 0. And let's say a new data write request has come. So it will increment to 4, which is 1, 1, 0. If you carefully look at this change, how many bits have changed? This bit remains the same. This bit remains the same. Only this bit has changed. That is, only the first bit has changed. So what are the possibilities? What are the misinterpreted bits that can be passed? Either you can pass 0, 1, 0 to the next domain. That is, both these bits are same and the third bit is also same. The third bit, the MSB has also not changed its value. Or else 1, 1, 0 can be passed. That is, both these bits are same and the third, the MSB bit has also correctly changed. So either you can pass value 3 or either you can pass value 4. There is nothing in between that can be passed, because the number of bits that subsequently changes only one bit. Only one bit is changed between two values. Between 3 and 4, only one bit has changed. That is the advantage in gray coding. That is, the number of bit changes is lesser as compared to binary coding, because of which the wrong interpreted pointer or incorrect bit propagation is minimized. Okay, so that is the reason why we are preferring gray coding instead of binary coding. And the second question we'll now answer is, why do we need two flip-flops? So we need two synchronizers in order to solve the problem of passing signals across the clock domain. Okay, so let's say your signal is coming to the two flip-flops, and as it is passed through this one flip-flop, the signal changes right before the clock edge at which this flip-flop is sampling. Okay, flip-flop 1 is sampling the data at a clock edge, and right before this clock edge, the signal 1 has changed. So what this will result in? This will result in a metastable value. That is, your flip-flop might not be able to determine whether it is a strong 0 or whether it is a strong 1. It will fluctuate in between. So that fluctuation has extra 1 clock period time to get stabilized before this flip-flop edge arrives. So before the second flip-flop edge arrives, the data might be stable. And this, why I'm saying might be, because what are the chances that even after two flip-flops the metastability persists? The chances are very less. That is why we are going with two flip-flops, because there is something known as MTBF. MTBF refers to your mean time between failures. Mean time between failures drastically increases as the number of flip-flops increases. For example, if I'm saying that there is the signal is being passed through one flip-flop and then it is passed to the other clock domain, then your failures can happen in a frequency. The failure frequency is very low. Okay, and if this is the case when I'm using one flip-flop, if there is one flip-flop, the failure probability will reduce to a very lesser value. If there are two flip-flops which are built as a synchronizer, my failure value will increase. The mean time between the failures, not the failures, the mean time between the failures will increase by orders of magnitude. If there are three flip-flops, then the mean time between failures can exceed your system lifetime. That means the failures, there is no probability that failures, the metastability failure might occur if you're using three flip-flops for the entire duration of when the system is being run. Mean time between failures refers to your, it tells you on an average that how many metastability errors might occur when your system is running. So if your metastability errors which are occurring when your system is running is very less, The mean time between them is very less. That means the failures are occurring very frequently. If the mean time between the failures is less, the metastability is occurring frequently. That happens in case you have one flip-flop. As the number of flip-flop increases, the mean time between the failures increases a lot. This means the metastability failure will occur very less frequently. That is the reason why two flip-flops is said to be completely sufficient to reduce metastability completely. Okay, so that's why we are not going with three flip-flop. Instead, two flip-flops are preferred because of this MTBF, and MTBF is calculated based on your number of flip-flops. It also depends on your clock frequency, your data toggle rate and all, but it depends on number of flip-flop also, and this is the standard design. Two flip-flop synchronizer is a standard design if you take a look at the literature for reducing metastability. Okay, and why do we need these synchronizers? Because we are passing the pointer information from one clock domain to the other to determine the full and empty conditions. We have seen that in the while we were discussing the architecture. So let's look at the pseudocode. So let us now understand the pseudocode of asynchronous FIFO. So this code is actually obtained from the site vlsiverify.com, and in that vlsiverify.com the entire implementation is written. The code is actually there in detailed format. So but here we will only discuss the pseudocode in a brief manner. So first let us understand the synchronizer code. The synchronizer, we have seen why do we need the synchronizers, because in order to determine the empty and the full flags, we need both the write pointers and read pointers. Since we need the we need to obtain the cross domain signals, it's important that in order to avoid any metastability issues, those signals are synchronized via the two flip-flops. Okay, so this is the code where two flip-flops are connected back to back. That is, if we set your Q1 and D out, the output of the two flip-flops are given the value 0. Else what happens? Your D in is passed to Q1, and at the same time your Q1 is passed to D out. So this is nothing but two flip-flops connected back to back, which is acting as a synchronizer. We have also seen why these two flip-flops are needed, and we have understood why, the concept of MTBF, the mean time between failures. So let's move on to the next part of pseudocode, which is the write pointer handler. So this is the pseudocode for write pointer handler. Now, in write pointer handler, we have seen in the architecture, while we were discussing the architecture, that W pointer, that is the write pointer, is available. So easily you can convert this, since this is binary write pointer, this can be easily converted to gray write pointer. Now, in order to calculate the full flag, we have seen that we need both the write pointer as well as the read pointer. But the problem here is the write pointer is there, it can be obtained with respect to W clock, because all the calculations in the write domain is with respect to W clock. But in read pointer, all the calculations for read pointer, everything is done with respect to R clock. But in order to determine full, I need both these pointers. So the value of this R pointer has to be synchronized from your read clock domain to your write clock domain, and that is what we have done in these lines. So we'll take a look at what all things we have to do while calculating the full flag. So the first line says that your B write pointer next is equal to B write pointer plus W enable and not of full condition. So what does this mean? Let's say you have this FIFO, and in this FIFO, my current location for a write pointer is somewhat here. Now there is another write request, so I'll increment my write pointer by 1 to the next location. So my write pointer will point to the next location to be written. So this is what is happening here. The B write pointer is incremented by 1, and how do I know that it is this condition should result in 1? That means I am able to write to the FIFO if and only if my FIFO is not full. If my FIFO is full, then it's not possible to write into the FIFO which is full. That's why this condition, that the FIFO must not be full and the write enable should be asserted. If both these conditions are true, this means this will result in value 1. So this equation will we cut down to b right pointer plus binary right pointer plus 1. So this b right pointer next is nothing but the updated right pointer by 1 if and only if my FIFO is not full and my write enable is asserted. Now we will understand how the conversion from your binary to gray coding is done. So we have seen that why we are moving with gray coding, because the bit changes from one domain to the between consecutive numbers is minimum in gray coding. So that is why we are going with gray coding. We have discussed this previously. Now how do I convert binary to gray code? You right shift by 1 and then you XOR with the existing binary right pointer. So let's take a small example to understand this conversion. Let's say my binary number, I'm doing binary to gray conversion, and my number here is 0010. So I am supposed to find the gray encoding for this. So what is this doing? This is right shifting my binary value by 1. So when I right shift this 0010 by 1, what do I obtain? I obtain 0001. Okay. Next, I'm supposed to XOR it with the same value. So if I XOR this with, let's do it here. Okay, I XOR this with 0010. Since these are different, I'll get 1. This is also different, I'll get 1. Both these are same, I'll get 0. And 00, I'll get XOR as 0. So what am I getting? 0010. So the binary conversion, binary to gray conversion for 0010 gives me the result 0011. So this has successfully converted my binary value to your gray value. So what is my B right pointer next doing? It is incrementing my pointer value. It is updating my pointer value by 1 if and only if my W enable, that is my write enable, is asserted and my full condition is false. And the conversion from binary to gray is being done by right shifting by 1, then XORing with the same value. Now the next important thing which we must do here is find W full flag. How do I find W full flag? So in order to understand this, let's take a small example. Okay, so let us say I have a FIFO. My FIFO depth is, let's say, 8. That means 8 locations I have in my FIFO. This is 0, 1, 2. This goes on till 7. So this is my FIFO. I have 8 locations in my FIFO. I am saying that my right pointer is, let's say, at location 0, 0, 0. So since my FIFO depth is 8, how many, what should be the width of my pointer? Width of my pointer should be such that it adequately represents the last location of my FIFO. So my last location of the FIFO is 7. So my pointer should be such that it can easily represent 7. So this means this should be log 2 8, which is 3 bits. So my pointer should be of 3 bits to adequately represent all the location address of my FIFO. Okay, this is your pointer width. That's why I have written a 000 with 3 bits. Now I'm saying that my right pointer is at location 000. My read pointer is, let's say, at this location. Sorry, my right pointer is at this location, that is 6th location. My read pointer is at 000 location. That means no reads have happened in the FIFO. I'm only writing in the FIFO, and I'm currently at 6th location. So I have written in 6th location. There is a new write request. My right pointer will increment to this last location. Right pointer is now 111. Okay, so initially it was 011. No, initially it was 0 2 1 2 2. Yeah, so this is 1108. So my right pointer was initially 6, it was 110. Now there is a new write request. It has incremented to 7. It is now 111. Now there is another new write request. So my right pointer will increment by 1, which is nothing but 111 plus 1, which gives me value 8. This is nothing but 8. Okay, so this basically wraps around to your first location. If you ignore this MSB bit, the last 3 digits represent 000. Ignore this bit, so you get the location 000, which is nothing but the first location. So you're sort of wrapping around as soon as you reach the end of your FIFO depth. Okay, so this can be further explained by my right pointer is 0, 0, 0. Sorry, my read pointer is 0, 0, 0. My right pointer is 0, 0, 0, and the MSB bit is 1. So I'm ignoring this MSB bit in order to find the location, which is nothing but the first location of 0, 0, 0. This is in case of binary. What if I want to see this in case of gray? In gray code, 0, 0, 0 remains as it is 0, 0, 0. My right pointer gray code will be 1, 1, 0, 0. Okay. So what changes did I see? My in binary, my last LSB is same, then this bit is same, this bit is also same, only the MSB is changing. In gray, this bit is same, this bit is same, this bit has been inverted, and let us assume there is 0 here. This bit is also inverted. So the first two MSB bits are inverted in case of gray, and only one MSB bit is inverted in case of binary. That is the reason, as you say, that as soon as your right pointer is equal to read pointer, given your first two MSB bits are inverted, since we are going with gray encoding, we are not doing binary encoding. I am saying if my LSB bits, all the three LSB bits are same, only the the LSB bits are same, and the two MSB bits have been inverted. This means I've achieved the full condition. That is, wraparound has happened, all the FIFO locations have been written. So this is implemented using this line. That is, W full is my gray right pointer next should be equal to gray read pointer, which is synchronized. The gray read pointer you're obtaining after it is synchronized from your read clock domain to your write clock domain. So I'm checking whether my read pointer is equal to my write pointer, but my MSB of my read pointer, the two MSB bits of my read pointer, should be inverted. So here, if you see, the number of total locations is 8. And the number of bits which I need in order to represent all the location correctly is 3 bits. But in order to understand about the wraparound condition, the inversion of the MSB bits, what is the length of the pointer? The pointer should be of 4 bits. Okay. So let's say pointer width is nothing but 4 bits in this case. Okay, because in order to understand this MSB case, the inversion of the MSB, I need 4th bit also. The 3 bits won't be sufficient to it will be sufficient to raise the empty flag, but it won't be sufficient to raise the full flag. In order to understand the wraparound condition of full flag, I need 4 bits and not 3 bits. That's why you can see that I have written one more 0 here, because there are 4 bits representing all the locations. So if I see one more 0 here, all the 3 LSBs are same, only the MSB bit has been inverted. And that is in binary. In case of binary, only one MSB is inverted. In case of gray, 2 MSB is inverted. So I can tell that my FIFO is full. So now at every passage of clock and every negage of reset, you check whether your reset is asserted. If reset is asserted, your binary pointer, gray pointer, and your full flag, everything is given the value 0. Else, the right pointer, the updated right pointer, that is the right pointer plus 1 is given, is updated. That binary pointer is then converted to gray. So gray pointer next is also the gray pointer is also updated with the uh, pointer next value, and full flag is also updated. The full flag is detected using these lines, and that value is also updated at every clock edge. So at every clock edge, your binary pointer, your gray pointer, your full flag, everything is updated. So this was your we understood how the right pointer handler is how the right pointer handler works and how the full flag is working. Next, we'll take a look at how the read. Now let's look at how my read pointer handler is working. So we have seen previously that my full flag is determined using in my write domain, and my empty flag is determined in my read domain. So this we have discussed during the introduction also. So this is on the similar lines as the previous right pointer handler. So let's look at how this works. So your binary read pointer next is nothing but binary read pointer value, whatever is your binary read pointer value plus 1. How is that 1 determined? I want whenever you are reading from your FIFO, your empty should not be asserted. That means your FIFO should not be empty, because if your FIFO is empty, it is not possible to read anything from that FIFO. So your empty should not be asserted and your read enable should be asserted. If both these conditions boils down to 1, if this condition boils down to 1, then only you can increment your read pointer to your next read pointer location. Okay, so binary read pointer next is nothing but binary read pointer plus 1 only and only if your FIFO is not empty and your read enable is 1. Next, this conversion, we have seen how the conversion happens. You're converting your read pointer from binary to gray. That is, you right shift by 1 and then you XOR it with the current value. So this we have looked at using an example in the previous case. Now, we have seen that the full flag was determined using the right pointer handler in the right in the right domain. In the read domain, we will determine the empty flag. So our empty is calculated. You simply check your read pointer is equal to your right pointer synchronized. Read pointer is available in the read domain without any problems. Your right pointers have to be synchronized from your right domain to the read domain. Then both the pointers are checked for your equality. If both the pointers are same, this means your FIFO is empty. So we can take a look at this condition. Let's say your read pointer is here, your right pointer is here, but you get a write request, so you increment to this position. Then you get another write request, you increment to this position. So your right pointer is currently at this location, but your read pointer is still at this location. Now you get a read request, so you move your read pointer to this location. Now again you get a read request, you increment your read to this location. So your read pointer as well as your write pointer both are at same location. This means you have written the data, you have also read the data. This is one way to understand this empty flag. If both your write pointer and read pointer are in the same location, this means my FIFO is empty. Why I'm saying this? Because initially both were at 000 location. I have written 3 data into the FIFO. I've written 2 data into the FIFO. So my right pointer has incremented to this position, the next position to be written. And similarly, I have also read the data from that FIFO. That's why my right pointer has incremented to the next location to be read. This means there are no more locations to be read. All the locations have been read. This means my FIFO is empty. The another way to understand this is if your FIFO, your right pointer as well as my read pointer both are at location 000. The simplest way to understand empty. If both are at 000, that means no data. Your pointer always tells you what is the next location to be read or what is the next location to be written. Since both of them are at 000, that means no data has been written nor the data has been read. So if both these pointers are same, this means it is at empty. The FIFO is empty. So previously also we have looked at that both the right pointers and read pointers were at 000 location, but in that case my full flag was asserted. Reason being my right pointer MSB was inverted, and that inversion we got using the wraparound condition. Okay, so the pointers width of the pointers in this case should be 4 bits. Since my there are 8 locations, the number of bits required to represent all these locations are 3 bits. But since in order I have to understand the inversion of this MSB also to understand to assert the full flag, that's why my pointer width should be 4 bits instead of 3 bits. Okay, so empty detection of this empty flag is quite simple. Now, this is also similar lines to the previous code. That is, at every passage of clock, you check if the reset is asserted. You give the value 0. Empty flag is also asserted. That means if reset is 1, your empty is asserted. You empty the FIFO. Else, you update the pointer value with this pointer next value, and you update the gray pointer value with the gray pointer next value. You also update the empty flag at every passage of the clock using the rempty value that is calculated here. So this was all about the read pointer and the read pointer calculation and the empty flag calculation. Next, we will take a look at the memory and we'll take a look at the top module, which basically integrates all these submodules into it. So let's look at the memory part. So memory part of this FIFO is quite simple. You perform the write and read on the desired location. That is, if at every passage of a W clock, because the writes are happening with respect to W clock. So whenever W clock is edge arrives, you check whether your FIFO is not full and your write enable is asserted. If both the conditions are true, this means the data can be written to the FIFO. So whatever data in you have, that is to be written to your FIFO, and the address is obtained using the write pointer, binary write pointer value. Here we have seen that the pointer width in previous case was uh, 3 plus 1, which is nothing but 4. 3 where the 3 is sufficient number of bits that can represent 0 to 7th location for a FIFO depth of 8, but you add 1 in order to account for the wraparound condition in case of full flag. So this MSB bit, in order to determine the address in the FIFO where data has to be written, you don't need your MSB bit, you just need the last 3 LSB bits. So this is pointer width minus 1 is to 0, tells me the last 3 bits. It doesn't account for the MSB bit. So all the explanation, everything I have given with respect to the FIFO depth of 8. As soon as your FIFO depth changes, your pointer width will change, but the essence should remain the same. That is, pointer width minus 1 is down to 0 will tell you the address information, can provide you the address information. Pointer width bit, the pointer width bit, that is the 4th MSB bit, is only useful when you're calculating the full flag. So it has no role while you're writing the data in order to determine the address. So whatever data is there, that is written to the concerned location in the FIFO. The read here is asynchronous, that is your data out, whatever whatever location or address from which the data has to be read is determined using this pointer width minus 1 is to 0. Again, the MSB bit is not important here because the 3 bits were sufficient to determine the address locations, all the address location. So from that address location of the FIFO, the data is read. So this is a very common way of reading and writing data, where read is asynchronous and write is with respect to the clock. So this is synchronous. I say that this is synchronous because your writing is happening with respect to a clock. That means the state of the system is changing only with respect to your clock. That's why this is synchronous. And read, since read pointer width, the right pointer at tells you in which location, from which location the data has to be read, and this B right pointer will change only when your empty flag is not asserted and your read enable is asserted. So all those in the previous read pointer handler, we have seen that read pointer will increment only on the basis of certain conditions, which are which we have ensured in the previous read pointer handler block. So again, we don't have to repeat those same conditions here. So simply an asynchronous read, a compact way of doing the read and write can be done. But this is synchronous since the write is happening only at every passage of with respect to a clock. That means the state of the system is changing with respect to a clock. Next, this is the top module, where your top module tells me there are 2 synchronizers that I need to use because your write pointer information has to be passed to your read domain. So whatever write pointer, gray write pointer, that is passed through the synchronizers, that is, it is synchronized with respect to your read clock domain and you obtain the synchronized write pointer. Similarly, your read pointer has to be passed to the write domain in order to calculate the full flag. So with respect to W clock, the write pointer is synchronized using the 2 synchronizers, and you obtain the read pointer synchronized. So this is the pointer synchronization. These two are nothing but these two are instantiating the synchronizers, the 2 synchronizers. Next, the pointer handler. We have seen the write pointer handler and read pointer handler. So in the top module, you are instantiating all these submodules, and FIFO memory is then called. So all these, the entire code binds together all the submodules to implement the asynchronous FIFO. Next, we'll discuss about the FIFO depth as the last topic in our entire discussion for asynchronous FIFO, and then we'll end the lecture. Now let us understand the concept of FIFO depth. So in the introduction, during the introduction part, we have discussed why do we need FIFO depth. Since the clock domains are working at different clock frequency, and you need to pass from domain A to domain, you need to pass the data from domain A to domain B, which are operating at different frequencies. So there might be chances that the clock domain, the production of the data production is at a faster rate as compared to the consumption by domain B. So there should be some storage mechanism that stores the intermediate data, because since the reading is slower, that is writing is faster in domain A, but the reading is slower in domain B, because of which there is a possibility that some of the data might be lost. So in order to prevent that, there should be some data storage capacity available in the FIFO, so that even though the reading is at a slower rate, still no data is lost. So that is where the requirement of FIFO depth comes into picture. Let us solve a simple and a very small numerical on this. So let's say my question is, let's say my writing frequency or my FA, that is the frequency of domain A, is 80 megahertz. Okay, and my reading frequency, which is the frequency of domain B, is nothing but 50 megahertz. So we can see that the domain A frequency is more than domain B frequency, because of which there is a possibility that data might be lost. So in order to prevent that, we'll find the FIFO depth. Now I'm saying that the burst length or the number of data items which are transferred at once is 120. Now I need to find, also it is also mentioned that there are no idle cycles in between. So what do I mean by that? No idle cycles in between means that all the items are written as well as read in the consecutive cycles. That means FA writes the data, FB reads the data. FA writes the data, then FB reads the data. So all this reading and writing are happening in consecutive clock cycles. So how do we find the FIFO depth? So we'll now find the solution to this. So the time that is required to write one data item by FA. Since we know that FA is writing the data and FB is reading the data. So the time that is required to write one data item is time required to write one data item is nothing but the time period of clock domain A, which is nothing but 1 by 80 megahertz, which is equal to 12.5 nanoseconds. Okay, and we'll now find the time that is required to write all the data. Since we have previously seen in the question that there are 120 data items which are passed, the burst length is 120. So since the time that is required to write one data is 12.5, the time required to write all the data, that is 120 data items, is 12.5 into 120, which is nothing but 1500 nanoseconds. Now we will understand what is the time required to read one data. So who is doing the reading? The clock domain B is doing the reading. Time required to read one data is 1 by the clock frequency of domain B, which is 50 megahertz. This is 20 nanoseconds. So 20 nanoseconds. So I'm writing at a speed of 12.5 nanoseconds. I'm reading at a speed of 20 nanoseconds. The reading is slower as compared to the writing. So there should be some intermediate storage. Okay. So for this means for every 20 nanoseconds, that module B is going to read one data in the burst. Okay. So now we will find out the number of data that can be transferred in 1500 nanosecond. So 1500 nanosecond is the entire duration of writing all the data items into the FIFO. So within that data item, how many data can be perfectly transferred? That means how many data can be perfectly written as well as read. So that can be found out by 1500 divided by 20 nanosecond, because 20 nanosecond is the time required to read one data, and the total duration is 1500 nanoseconds. So this comes out to be 75. This means 75 data items can be written as well as read within the consecutive cycles without any idle cycles in between. And this can be the number of data items that can be read within this duration. Within this duration, I know all my data, 120 items are being written. Now within this duration, how many data items can be read? That you find it out by dividing the time period of domain B, which is 20 nanoseconds, and you get 75. So 75 items can be read within this duration. Now, so what are the remaining items? We know that the burst length previously mentioned in the question was 120, and within the time duration of 1500 nanoseconds, I was able to read 75 items. This means 45 items remaining are uh, remaining has to be stored. So these 45 items will tell you what is your FIFO depth. This means my FIFO depth or the FIFO should be capable of storing the remaining 45 items till the time my clock B is reading the data, because my clock B is slower at reading the data, so it will read 75 items, but you need some storage mechanism to store the remaining 45 items so that no data is lost in between. I hope this is clear. So in this video, we have seen why we need asynchronous FIFO and what are the application areas. We've also taken a look at the architecture where we discuss about metastability and why we need gray encoding instead of binary. And we have also understood the synchronizers, why two flip-flops are needed synchronizers, and also briefly looked at MTBF or mean time between failures. Next, we have taken a look at the pseudocode where your all the sublogs are explained using the write pointer, read pointer handler, full flag, empty flag, how those conditions are obtained, and all the FIFO memory synchronizers. All those we looked at, the submodules we have looked at in pseudocode. Next, we also understood the numerical. In order to understand FIFO depth, we are taking a look at a simple numerical. So if you liked the video, please share and subscribe. And in case of any questions, please comment down below. I hope you have enjoyed the video. Thank you.